The title of my talk today is about natural fibers and the flex fiber reinforced polymer composites in construction, properties, application, and challenges. So at a glance, it looks like a very specific topic, but it will touch on a very broad and very important topic for the future of construction. How can we design materials both saving and sustainable? So when I first began my work on using fiber-reinforced polymer composites in construction in 2011 in New Zealand, I never imagined how fast this field explored. So nowadays, for the construction industry, we face a dual challenge. On the one hand, we're asked to continue to deliver materials or structures which are safe, durable, and efficient. On the other hand, we need to reduce the environmental impacts towards the use of sustainable building materials. In this regard, the plant-based natural fibers, especially in the flax fibers, are fascinating material, which provides the opportunity to address both sides of challenges. To guide you through this talk, I have divided my presentation into 5 parts. First of all, I will give a brief introduction about my research institutions, Fraunhofer WKI and EBM-BTU Braunschweig, where those research are conducted. Next, I will ask the questions: what are natural fibers, and why? Why should we use plant-based natural fibers like flax as a replacement of synthetic fibers such as glass? The third part of my talk is about the properties of the flax itself, from the flax fiber to yarn to fabrics and the fiber reinforced polymer composites, and how the flax fiber reinforced polymer composites behave under the hygrothermal environment conditions. Afterwards, I will talk about the application of the flax FRP composites in constructions with examples and lessons we learn from the pilot projects. At the end of my talk, I will address the challenges and the outlook. What barriers remains? How could we move forward towards a wider adoption of natural fiber reinforced polymer composites in the construction? All right, so let us get started from a very brief introduction about my organization. So for those of you who are not familiar with the Fraunhofer Society, it's the EU's largest organization for applied research, employing nearly 32,000 staff across 75 institutions in Germany. So the Fraunhofer Society operates an annual budget of 3.6 billion euro, with 3.1 generated by the contract research. So the Fraunhofer Institute for Wood Research is one of those institutions located in, wait a moment. So located mainly in Braunschweig and Hanover and Wolfsburg, with the sustainability as the central focus for over 75 years. So we have 6 scientific departments working on forest, wood, material testing and certification, as well as the recycling and processing of building and construction demolition wastes, and the indoor quantities, of course, for the structure application. So last year, we had 53 publications, 5 doctor graduates, and 2 patents, generated a revenue of over 30 million euro. Regarding the TU Braunschweig, is one of Germany's oldest university and a member of the TU9, alliance of the 9 leading technical university It hosts the Institute of Building Materials, Concrete Construction and Fire Safety, so IBMB in German, which is the largest institution at the Faculty of Architecture, Civil Engineering, and Environmental Science. So at my institute, EBMB, we have some state-of-art testing facilities, like the very unique 30 million Newton tensile and compression machine for stay cables. We also have the Europeans leading 5 testing facilities with the capacity of heat release rate up to 20 million watt. So let we move on to the questions. What are natural fibers? Why should we use flax fibers to replace glass fibers for composite application? So first of all, I will give a brief introduction about the classification of the polymer matrix and the fiber materials. So based on the response to heat, so the polymer matrix can be divided into the thermoplastics and the thermocells. So in general, the thermocells has better tensile properties, durabilities, and thermal stabilities, which are suitable for the civil engineering application. For example, like the epoxy. So for the fiber materials, we have synthetic fibers, like the glass fiber, carbon fiber, aramid fibers. For natural fibers, mainly based on the fiber origin, we have mineral-based natural fibers. So nowadays, it's mainly the basalt fiber, which is widely used in the civil engineering. And the animal-based natural fibers, like the silk and the wool, and the plant-based natural fibers. So the focus of this talk, flax, jute, and also wood. So wood is also a kind of plant-based natural fibers. So why should we use plant-based fibers? First of all, they are renewable resource, comes from the agriculture waste, using them to support the circular and bioeconomy development. It has the potential to reduce the greenhouse gas emission, and normally the production of the plant-based natural fibers is a less resource-intensive process with less water, energy, and waste generated. So natural fibers are readily available everywhere. They are lightweight, cheaper compared with the synthetic fibers such as glass. Most important, the specific mechanical properties of some plant-based natural fibers, for example, which are very comparable to those of the glass fibers. So in this table, we can see the production of 1 kilogram of the flax. The energy needed is much lower compared with other synthetic fibers, such as glass. So overall, the flax fiber offers a much lower energy footprint and a clean environment advantage compared with synthetic fibers to be used in the composite engineering. Why is flax? So in this table, you can see I listed dozens of plant-based natural fibers. If we take a look at the tensile strength of the plant-based natural fibers, so the flax has the highest upper limit in the tensile strength, up to 2000 megapascal. So which is relatively close to that of the e-glass fiber. Let we take a look at the specific modulus, for example. So the flax fiber has the specific modulus higher than most of the plant-based natural fibers, which is even higher than that of the e-glass fibers, as you can see here. So that's why the flax fibers combines the lightweight, renewabilities, and the glass comparable stiffness, so making flax fiber highly attractive for the composites in construction application. Let's move on to the comparison between the flax fiber and the glass fiber. So in this table, I gave the chemical compositions of those widely used plant-based natural fibers. As you can see, for the different plant-based natural fibers, they have different chemical compositions, like the cellulose, hemicellulose, pectins, lignins in different quantities. So this diversity gives the independent fiber with completely different mechanical performance and durability. By contrast, so the glass fibers has a stable chemical consistency, which is mainly dominated by the silicon, around 15.4% to 65% with other different oxides to change the function. So how about the comparison between the microstructure between the flax fiber and the glass fiber? Let we take a look. So for the glass fibers, which has a very unique structure. So you can see very smooth surface. The diameter is quite constant along the length. But for the plant-based natural fibers, like a flax fiber, which show high variation, so you can see the existence of the natural defect, like the kick bands and the long continuous diameters along a flax fiber. And also you see the irregular cross-section of the individual fibers. Towards the manufacturing process, now I would like to answer the question how flax fiber or flax fabrics are produced. So in this slide, you can see the production chain of the flax fiber started from the harvesting of the flax plants. After the drying process, the stalks of the flax plants go through the ripping process to remove the seeds, and then the reading process to separate the pectins. After that, go through the drying process once again. So the stalks of the flax plants were broken and scorched, hacked. So we get the packet final short fibers. So the short fibers can be further processed to be fabrics for the composite application. So short fibers are spun into the yarns, and the yarns are woven into different fabrics for engineering application. So in my institute, we have the textile machine, which allows us to design fabrics with different texture. So let we take a look at the manufacturing of the glass fibers. So I would say the production of glass fiber or glass fiber yarns is a industry standardized process. So the known materials like the silicon, calcium oxide are mixed, melted at the furnace at a temperature of about 1,700 degrees Celsius to form a homogeneous glass. After that, refined and joined to be the glass filaments with very constant and structures. So the comparison here, we can see the glass fibers on the one hand are chemically consistent, have a very uniform structure, are highly standardized industry process, which contributes to the predictable performance and the consistency in design for the engineering application. But for the flax fibers, have high natural variation in the chemical composition, moisture. The production involves the biological process like the retting process and like the mechanical process, like the right. So which leads to much more variabilities to manage and control. So after the comparison between the flax and the glass fibers, that we take a close look on the mechanical performance of the flax fiber, yarn, fabrics, and FRP composites. So in this slide, we can see flax is a multi-scale material. At the microscope level, the stem of the flax plant is composed of the bark, fiber bundle, and the xylem. So at the mesoscope level, each individual flax fiber bundle contains dozens of elementary single fibers which are connected at the middle lamina. At the microscale level, we can see the multi-cell wall structure. So the primary cell wall, secondary cell wall, which is encodes the lumen. At the nanoscale level, we see the chemical compositions which are bonded together, meaning the cellulose and the pectins and the hemicellulose. So let we move on, have a close look on the fiber bundle. So the fiber bundle is the components we used to extract flax fibers to produce textiles. So as you can see, under the microscope, we can see the individual flax fibers, which are connected at the so-called middle lamina by the pectin. And for each fibers, they have multi-cell structures, which will be discussed further in the coming slide. So let we take a look. So in this case, you can see the schematic of the flax single fiber, so which is mainly composed of the primary cell wall and the secondary cell wall. And the secondary cell wall is enclosed the hollow lumen. The lumen is responsible for the water uptake. For the secondary cell wall, it can be further divided into S1, S2, and S3 layer. So the S2 layer has the largest thickness, contains most of the microfibres. So the cellulose microfibres are the components determine the tensile strength and the tensile modulus of the flax fiber. So those microfibres are further orientated with an angle around 10 degrees with the longitudinal direction of the fiber. So this microfiber angle also determines the mechanical performance of the fibers significantly. So in general, a plant-based natural fiber has a smaller microfiber angle, the tensile strength will be higher. The tensile strength will be small. So afterwards, let we move on to the tensile properties of the single flax fibers. So the flax fibers are extracted from a yarn of unidirectional flax fabrics. So in this tensile stress strain curves, we can see the significant scat of the results. On average, so the tensile strength of the single flax fiber is around 850 to 1000 megapascal. The modulus is about 15.5 to 16.3 gigapascal, and the failure strain is about 2%. So the tensile strain and the tensile modulus are respectable. But what stands out are the coefficient. So as you can see, for the tensile strength, the coefficient of variation is very large, up to 15%. For the modulus and the strain, is between 20% to 13%. Why? In this figure, we can see some of the reasons for that. So you can see the flax fiber tested under the microscope. You can see the existing of the fiber bundles and the long continuous or the irregular distribution of the fibers. So that's the reason for the significant scar of the properties. Next, let we move on to the flax yarn. So the flax yarns are also extracted from the same fabric. So as you can see, the tensile strength is about, the average tensile strength is about 600 megapascal. There was a significant reduction from the 800 to 1000 for the single fiber. And also there was a significant reduction in the modulus of the elasticity compared with the single fiber. But what is interesting is the reduction in the coefficient of the variation. So from the 20 to 50% of the single fiber dropped to 11 to 13%. What's that mean? So which means when we twisting the short fibers into yarn, we will be able to reduce the variation, make the properties much more predictable. Let we continue and move on to the tensile properties of the flax fabric, the unidirectional flax fabrics. So as you can see, the further reduction in the tensile strength from 600 megapascal of the yarn to roughly 2010 megapascal for the fabric, and the modulus are also reduced significantly. Well, it's quite interesting. Yeah, let we take a look at the coefficient of variation, less than 10%. So from the evolution of the mechanical properties of the flax fiber to yarn to fabrics, we can see the absolute values like the tensile strength, tensile modulus decrease, but the behavior becomes much more predictable and consistent. So this is a clean advantage of using flax fabrics for engineering design and structure application. So in this slide, I would like to give you a general information about the tensile properties of the flax fabric reinforced polymer composites. So, as you can see, for the one layer flax fabric reinforced polymer composites, the tensile strength is about 228 megapascal, and the modulus is about 12 gigapascal. If we increase to 2 layers of the flax FRP, we will be able to increase the strength and the stiffness significantly. So in this slide, this figure, you can see the tensile stress and strain curves of the epoxy, the flax fabric, and the flax fabric reinforced epoxy composites. But what I want to say is the sensitivities of the flax fiber and the epoxy to different environment conditions. So in this figure, you can see the flax fabric tested in tension at the dry condition. So the blue line is the flax fabric after 24 hours of exposure to water and tested in the wet condition. So there was a significant reduction in the Young's modulus, a slight increase in the tensile strength of the fabrics. So in this figure, we can see for the post-cured epoxy coupon, when the epoxy coupon tested at the standard condition, 20 degrees Celsius, 65% relative humidity, the tensile strength can up to 8 megapascal. But if the coupon tested at 17 degrees Celsius, we can see the significant reduction in the tensile strength for the epoxy itself. So what kind of information we can get from here? So when flax epoxy composites offer good performance, but we need to be very careful and consider about the environmental exposure and the curing conditions when designing natural fiber reinforced polymer composites for the real application. So let's move on to the hygrothermal aging on the flax epoxy composites at a different environment condition. So in this figure, it shows that the flex epoxy composites exposed in the 17-degree oven for 6 weeks. So here is the reference samples without the 17-degree exposure. And those curves are the samples exposed at the 17-degree for 6 weeks. We can see compared with the reference sample, there is even a slight increase in the strength and the stiffness. Let we move on to take a look flex FRP composites exposed to water at room temperature for 6 weeks. So you can see compared with the reference samples, there was a significant drop in the tensile strength. So let us take a look how the flex FRP composites behave at the 17-degree Celsius but water condition for 6 weeks. So compared with the reference samples, there was a further reduction in the tensile strength. So those results highlight the moisture is the main enemy of the flex epoxy composites. When temperature, of course, below the glass transition temperature of the epoxy are low, it's tolerable. But the heat plus the water accelerated the degradation of the fiber reinforced polymer composites significantly. Let we have a close look of the hygrothermal aging effect on the flex epoxy composites over different exposure times. So the left figure gives the flex FRP composite tensile strength exposed to 17-degree oven condition. So as you can see, compared with the reference samples, after 3 months, there was only small reduction in the tensile strength, 8%. For the flex epoxy composites at the room water conditions, so compared with the reference after the 3 weeks, the reduction is also very small. But when we exposed the flex FRP composites at 17-degree water conditions, even in the first months, we can see a 23% drop in the tensile strength. So after 3 months, further reductions also observed. Let we take a look at the E modulus of the flex FRP composites over time. So for the E modulus, compared with the reference sample exposed, the samples exposed at 17 degrees, we can even see a slight increase in the modulus. For the composites exposed to water room temperature, so you can see the significant reduction at the month 1 and the month 3. For the composites exposed to 17-degree water conditions, in the first month, there was a 32% drop in the modulus. Afterwards, further serious reduction in the modulus. So those results tell us flex epoxy composites tolerant modest temperature, but water, especially hot water, can result in a rapid loss of the strength and the stiffness over the time. How about the hygrothermal aging effect on the flex fabrics? So for the first row, we already discussed that we take a look under the same exposure environment conditions, how the tensile strength of the flex fabrics will change. So as you can see, for the flex fabrics exposed to the 70-degree dry condition, almost no change in the tensile strength. For the flex fabrics exposed to water but room temperature. After 3 months, there's even some increase. For the flax fabrics, exposed to 17-degree hot water conditions, there are some fluctuations in the property, but the change was quite small. So that's why we can make a conclusion here. Flax fabric is quite robust under the hygrothermal aging, but when the fabrics are combined with the epoxy matrix and the fiber polymer matrix interface becomes the link weak. So after the exploring the mechanical performance of the flax, that we move on to the potential application of flax fibers. Flax fiber reinforced polymer composites in the construction. What we can learn, the sustainabilities and the performance of them can bring real impact. So one of the promising application of flax FRP composites is to be used in the so-called concrete field FRP tube structure. So the flax FRP serves as the cast-in-place formwork for the fresh concrete and also provide the additional confinement to the concrete. The core can be further reinforced with some natural fibers like the coconut fibers. So in this tensile stress and strain curve, we can see compared with the plain concrete, the use of the 2-layer, 4-layer flax FRP able to increase the node carrying capacity and the energy absorption capacity significantly. We know recycled aggregates concrete is a sustainable approach if to be used for the new construction application. However, compared with the normal aggregates concrete, the recycled aggregates concrete normally has much lower compression strength and show larger variation in the compressive properties. So use the flax FRP tube as an extra confinement. We will be able to increase the compression strength and the ductilities of the concrete significantly, and also reduce the variation, as you can see from those results. Another application of the flax FRP is as the external strengthening material of existing reinforced concrete structure. So we used the U-shape and the L-shape flax FRP sheet to reinforce the concrete beams. As you can see in the node and the deflection curve, compared with the reinforced concrete beam, the use of 4-layer or 6-layer flax FRP are able to increase the node carrying capacity, the ductility, and the energy absorption capacity significantly. It's quite interesting to point out that for the flax FRP reinforced RC beam, the typical failure is the rupture of the flax FRP, so which means the full tensile strength of the composite can be used. But for the traditional glass or carbon FRP strength, the RC beam, we know the debonding is always a critical issue. Another application is to be internal reinforcement of concrete, to be the textile reinforced mortar or textile reinforced concrete structure. So we use the epoxy-coated flax mesh as the internal reinforcement to increase the node carrying capacity of the concrete and to modify the crack distribution of the concrete. So this is an interesting example to use the flax mesh to develop the textile reinforced mortar, the so-called flax ship at the German concrete color competition with our student. And another promising application is the combination of flax FRP with wood to be hybrid wood system. So here you can see in this node and deflection curve, the use of the flux FRP will be able to increase the node carrying capacity of the wood. And in our research group, we also carry out the long-term durability test of full-scale flex FRP wood, carbon FRP wood, and flex glass hybrid FRP wood panels exposed to the natural aging and sustained loading up to almost 2 years. So those long-term tests showed promising results of using flex FRP to combine with wood for hybrid system application. So the last potential application of the flex FRP is as a skin material with a lightweight core for sandwich structures to be used for panels, facade, and those applications. So as you can see, the combination of flex FRP with the balsa wood core with the XPS. Of course, fire safety is a very critical issue for the application of natural flex FRP composites for the construction. So in our team, we did a lot of research to improve the fire performance of flex fabric reinforced polymer composites and also with wood. So after the discussion about the potential application that we move forward, how those concepts can be realized in the practice. So in the next part, I would like to show some pilot projects using flex fiber reinforced polymer composites in the reality to show the feasibilities and the performance of the flex FRP composites for the practical application. The first pilot project is a 40-meter footbridge was opened in Netherlands in 2016. So the composite bridge has a weight of 1.5 tons, which is very lightweight, which is made of the non-woven hemp mat flex fabrics and the PLA foam core, as you can see here. So the mat fabrics and the PLA foam are bonded by the bio-resin using the vacuum infusion process. So in this table, you can see the different materials used for this bridge. This is the first large scale demonstration of biocomposites in the infrastructure application. In 2020, the world's first biocomposites movable bridge was opened in Netherlands. So as you can see here, so this bridge includes two 22 free span and another 22-meter composite deck. So the in total 66 meter of the biocomposite road surface. So the composite deck consists of 80% of the bio-based material from flax, fibers, fabrics, and the balsa wood. Another 20% from the glass fibers. So this bridge was designed for 15 years of application. It is expected at the end of the surface life, the bridge can be used as a fertilizer. So this bridge also allows for the ships to pass by up to 70 meter wide. So this bridge is mainly designed to carry the cyclists, but also for the occasional cars transportation. Compared with the older concrete bridge of 400 tons, so the composite bridge is about 13 tons, which reduced significantly. So over 20 sensors were implemented to monitor the long-term performance. And of course, coatings are used to prolong the durabilities of the flex fiber reinforced polymer composites. So here you can see the road surface of the composite deck. In 2022, Still in Netherlands, the smart circular bridge #1 was opened. So this is a 50-meter padding string and a bicycle bridge made of flex fabric composites in a bio-based polyester. So the full composite deck is made of the flex FRP and the PUR foam, and the robot wood flex FRP are used to be the handrail of this project. So in total, about 3.2 tons of the flex fabrics were used, designed for 15 years. And real-time monitoring using sensor networks to understand the long-term performance. All right, so let we move on to the last pilot project. The second smart circular bridge opened in Ulm in Germany this February. So this is a 8.5 meter long, 5.3 wide span padding string and the bicycle bridge. So mainly made of the flex fabrics, also in a bio-based polyester resin. So the bio content of the resin is increased to 60%. And the bridge itself is very lightweight, just 3.9 tons, but very important is to know the bridge can carry 24 tons of load, and the bridge is approved for vehicle transportation every day up to 12 tons. The robust coatings are used to improve the durabilities, but this project was initially criticized by the Taxpayer Association in Germany, as the cost have risen from the original 33,000 euro to 313,000 euro to 618,000 euro at the end. So there was a calculation and a comparison between the conventional bridge made of the steel girders and the wooden surface. There was a 28% increase in the budget. So let we have an overview of those 5 bridges from the initial footbridge to the weather's first movable bridge, and now to the Ulm bridge, right? Which are even suitable for the transportation of the cars. So we can see the advancement of the development of the bio-based composite bridge in the past few years. Those pilot projects show the high potential of using flex fiber reinforced polymer composites bridge for the infrastructure application. But on the other hand, we also need to be very careful about the challenges to use those materials. So let we take a look. I think the first major challenge is the large material variation. We know the variation in the mechanical properties at the fiber level. So even through the variation reductions at the yarn and the fabrics, it still remains high compared with the carbon fiber or glass fiber. So in this case, we have difficulty to predict the materials properties accurately. And another problem is about the manufacturing. Compared with the synthetic fibers, because of the hollow structure, microstructure of the natural fibers, it becomes typically hard to have a uniform fiber alignment, resin impregnation, and avoid free elements. And we know the natural fibers, they absorb the moisture, leading to the swelling, matrix, and fiber debonding. This could be an issue for synthetic fiber as well. But from the hygrothermal aging test, we see that the significant reductions in the strength and the modulus over time, particularly in the wet and the warm conditions. And the fire safety is a critical issue for all kinds of nature-based material, like the flax, like the wood. And compared with the glass or carbon carbon FRP, the flex FRP typically has a lower stiffness, which is about 10 gigapascal. For the strength, is about 250 megapascal, so much more much small compared with the glass or carbon FRP. And even there are some pilot projects existing. There are knockoff established design codes, the testing standards for the durability, and which has the wide adoption in the mainstream construction. And also it should be pointed out that due to the inflation in the past few years, the bio-based fabrics are increased, the cost are increased significantly. So as you can see, the pilot projects show that the cost could be higher than the conventional steel or concrete bridges due to the small scale production, the high resin cost, and the limited industry supply chains. But myself, I'm quite confident there will be a promising future for the use of natural fiber reinforced polymer composites in construction, because the pilot projects in Netherlands and Germany already show the advancement from the pedestal bridge to the movable bridge and even to the vehicle capable bridges. So those real-world examples build confidence in performance, durabilities, and monetary strategies for using them. And we also focus on the smart design to fully reuse or safe dispose of the bio-based structures after the surface life. And now we have a lot of supportive policies. Like in Germany, we have the national bioeconomy strategies, and the growing demand for sustainable building materials are driving the adoption. As the manufacturing scales up, cost will decrease. This will make the natural fiber reinforced polymer composites more competitive with glass fibers. In my vision, so the natural FRP composites may not replace the steel or carbon FRP fully, but they will become highly attractive for medium-span bridges, pedestrian infrastructure, facade, module housing, and the hybrid system where sustainability is important. So overall, the challenges are the high material variation, the durability issue, fire safety, and the economics. But the outlook is promising. So with the growing pilot projects, the hybrid designs, and the smart monitoring will pave the way towards wide adoption of natural fiber reinforced polymer composites. So in my institute, we are not just using the natural fiber reinforced polymer for construction. We are also doing sports products with natural fiber reinforced polymers, and also for the automotive engineering. So like the service production of the Porsche 911, those cars are made by us from the natural fiber reinforced polymer composites. So to the end of my presentation, so I would like to thank the co-authors who contributed to this presentation and the technical and financial support from my institutions and the different funding agencies. So thanks a lot for your attention.